I became a physicist because I've always been fascinated by big questions. For instance, like how the universe came into existence. It's generally accepted that the answer is the Big Bang, but there are some people who think that there exists data that disproves the idea, specifically a star that is reported to be older than the universe. And that actually would be a big deal and is definitely something we need to understand better. It's often said that if the title of a video is a question, the answer to that question is no, and it's true of this video as well. But you knew that already. If the Big Bang had been disproved, it would have been a huge deal, and you'd have heard a ton about it in the press. But the claim that a star exists that is older than the universe is an interesting one, and it's important to understand the entire conversation. So let's dig a bit more deeply. What are these Big Bang skeptics claiming? Well, first and foremost, they're not using sketchy data. They invoke well-accepted scientific claims. For instance, the scientific community has used a vast array of data and settled on an age of the universe as the very precise number of 13.799 plus or minus 0.021 billion years. This number is generally accepted among cosmologists. Scientists also have determined the age of a star with the boring official name of HD 140283. This star has the oldest, well-determined age of any star in the cosmos. It is located about 200 light-years away, and astronomers have pegged its age at 14.45 plus or minus 0.8 billion years. Because of this star's exceptional age, it is often referred to as the Methuselah star, named after the biblical patriarch who the Old Testament claims to have lived for 969 years, the oldest of all biblical figures. So how is it that astronomers have determined the Methuselah star to have been so old? Well, to understand that, you have to know that there are 3 different known populations of stars, 1, 2, and 3. Our own Sun is a member of population 1 stars. The Methuselah star is a population 2 star, and population 3 stars are merely hypothetical. No population 3 star has been observed. The distinction between the 3 different populations is the amount of heavier elements found in them. This is directly related to when the stars were formed. Immediately after the Big Bang, essentially only hydrogen and helium were present. If you counted atoms, the universe was about 92% hydrogen and 8% helium. If instead you weighed the substances, hydrogen made up about 75% of the matter of the universe and 25% was helium. This is because helium atoms weighs about 4 times as much as hydrogen ones. The first stars in the universe were population 3 stars, and they were made of this primordial mix. Current thinking is that they were huge stars that lasted only a few million years, furiously fusing hydrogen and helium into heavier elements. Because these stars were so huge, they lived fast and died young as spectacular supernovae that blasted their contents across the cosmos, including a smattering of heavy elements. Those heavy elements mixed in with the primordial hydrogen and helium, and it is this polluted mix of gas that collapsed to form population 2 stars. The process repeated itself with the population 2 stars. As the larger ones died, they also seeded the cosmos with even more heavy elements. From that murky mix of elements condensed the population 1 stars. This mix of elements led to planets and even us. This is why Carl Sagan often said that we are all star stuff. So, like I said, the Methuselah star is a population 2 star. To determine its age, astronomers needed to determine its brightness and what the ratio of concentration of heavier elements to hydrogen was in its outer layers. And of course, they modeled how its fusion over time affected its elemental makeup. Of special interest is the amount of oxygen and iron, as these are elements that are prominent components of different stellar fusion processes. The Methuselah star was first studied in 1912, where it was initially noted to be very deficient in iron and, to a lesser degree, oxygen. Earlier measurements of the star's brightness and chemical content led to estimates of the star's age of upward to 16 billion years old. However, over the following century, better and better measurements of the star's distance resulted in better estimates of its brightness. In 2013, a precise measurement of the star's distance by the Hubble Space Telescope led to the estimate for the star's age that I quoted in the beginning of this video. The biggest contribution to the uncertainty in the star's age is no longer a determination of the star's distance, but rather its oxygen content. I put a link to the paper that detailed all of this in the video description if you want to know the details. A second estimate for the age of the Methuselah star was published in 2014. This estimate was a bit younger, specifically 14.27 billion years, with the same uncertainty of 0.8 billion years. I put a link in the description to that paper as well. But no matter which estimate you use for the age of the Methuselah star, you can't help but notice that they are both older than the universe, which is an obvious problem, and one on which people who dislike the Big Bang often point to as a fatal flaw. However, the people who do that seem to have a misunderstanding about data and, most importantly, uncertainties. Let's unpack both of those factors. When you measure something, you never know the true value. Your measurement is just an estimate of the true answer. So let's take the age estimate of the Methuselah star of 14.45 plus or minus 0.8 billion years. We don't know the true age of the star, we just know that it's in the neighborhood of 14.45 billion years. And those uncertainties are important too. If you add and subtract the uncertainties to the estimated age, you find that the age of the star is between 13.65 to 15.25 billion years. Technically, what we know is that there is a 70% chance that the true age is in that range. And yes, that means that there is a 30% chance that the true age of the star is outside that span. That 30% split is half higher and half lower, which means that according to astronomers' best estimates, there is a 15% chance that the true age of the star is lower than 13.65 billion years. This is, of course, younger than the accepted age of the universe. And if you properly compare the estimates of the age of the star and the universe, you find that the current estimate for the age of the Methuselah star means that there is about a 20% chance that its true age is lower than the best estimate of the age of the universe. Ballpark, that's about the same as flipping a fair coin twice and having it come up heads both times. It's really not so unlikely. So, the bottom line is that there really isn't a strong disagreement between these measurements of the universe and the Methuselah star. Statistically speaking, there's a very good chance that the star is younger than the universe, which, of course, it has to be. Now, this doesn't mean that the question is 100% resolved. What researchers need to do is to do a better job estimating the age of the star, and astronomers will also revisit the estimate for the age of the universe. There is reason to believe that an ongoing conversation about the speed at which the universe is expanding might lead to a revised estimate. I made an earlier video about that mystery. That might sound like an unsatisfying conclusion where the estimate of both the age of the star and the universe might change, but that's science for you. Scientists don't have a preconceived answer when they do a measurement, and they have to always be open to refinements as future data comes in. But the bottom line is that when one properly compares the accepted age of the universe and the Methuselah star, and properly takes into account the uncertainties, there is no cause for concern, and most certainly, the age of the Methuselah star isn't a smoking gun in the case against the Big Bang. So there you have it. The supposed conundrum isn't a conundrum at all, something which we solved using sound physics principles. And that should surprise no one, as I've always said, physics is everything.